Right, this video is on oxidation and reduction reactions and overview. It's also on calculating oxidation numbers and then using oxidation numbers to decide if something is an oxidation reduction reaction or not. Okay, so what are oxidation and reduction? Technically, they are it's a type of reaction broken up into sub-reactions that occur together, which is kind of a complicated definition, but it is a broad category of reactions, just like things like precipitation reactions, acid-base reactions, synthesis, double replacement, all of that kind of stuff. And they actually occur, the oxidation reaction and the reduction reaction occur together within the same big reaction. So you can't have oxidation without reduction, and you can't have reduction without oxidation. So what are they? Oxidation, you might think it involves oxygen, and that's actually what early chemists thought too, but a lot of other things can be oxidized other than just oxygen. Oxidation is actually just defined as the loss of electrons. That's all oxidation is. And maybe you might guess that reduction then is the gain of electrons. How are you supposed to remember this? Is this just another memorizer in chemistry? No. There's several ways that teachers teach to remember this. I teach it like this. It's a silly little phrase, oil rig, which you might say that means nothing to do with chemistry, and it stands for oxidation is losing, right? O-I-L, oil, and then reduction is gaining. R-I-G. So it's like an acronym. It's silly. It doesn't mean anything. It's just supposed to help you remember that oxidation is the loss of electrons and reduction is the gain of electrons. You can't have the loss of electrons unless something's gaining, and you can't have the gain of electrons unless something is losing electrons. And so that's why oxidation and reduction occur together. For short, we call them redox reactions because redox is the reduction part of the word and then the oxidation part of the word. So you might hear me or another teacher call them redox reactions, and what that really means is that it's an oxidation reduction reaction, same thing. Okay, we've just established that oxidation is the loss of electrons and reduction is the gain of electrons. They occur together. And so it could be something as simple as this. Like when we first learned about ionic bonding, I didn't tell you that then, but ionic bonding is actually oxidation and reduction because you have somebody losing and somebody gaining electrons. So if you think about when magnesium, who comes in with two valence electrons, we'll draw them as dots almost like in Lewis structures, reacts with sulfur, who has 6 valence electrons, we know that magnesium gives its 2 electrons to sulfur, right? Resulting in the magnesium plus 2 ion and the sulfur minus 2 ion. And this is actually an oxidation and reduction reaction. Magnesium losing the electrons became magnesium plus 2, and sulfur gaining the 2 electrons became sulfur minus 2. And so this is the oxidation reaction and this is the reduction reaction. Again, oxidation is losing, reduction is gaining. They occur together. They're actually called half reactions because the half reaction of oxidation and the half reaction of reduction go together to give you the full, complete oxidation, reduction, or redox reaction. And so that's a very simple example of an oxidation reduction reaction that we can understand at this time without going further into this, as an initial example. It does get more challenging than that, but before we do that, we have to learn about things called oxidation numbers. And so oxidation numbers are a positive or a negative, I don't want to call it charge, number assigned to an atom to indicate its degree of oxidation or reduction. So we're going to use eventually, once we know how to do this, oxidation numbers to determine, one, whether or not a reaction is a redox reaction, and two, to determine who's being oxidized and who's being reduced, and then what the oxidation half reaction is and what the reduction half reaction is. So there's more than a couple rules for assigning oxidation numbers. Luckily, a lot of this will sound very familiar to you. So there's a couple general rules, and then there's some more specific rules. The first general rule is that, for ionic compounds, goodness gracious, group 1 and 2 metals will have an oxidation number equal to their ionic charge, meaning sodium's oxidation number will be +1, magnesium's oxidation number will be +2, just like we know charges to be. And then the second rule is that the most electronegative element will have the oxidation number equal to its charge. And so I will explain all of this because right now I know it doesn't make a whole lot of sense after we go through these other examples. So, some other rules for assigning oxidation numbers. If you have an elemental atom, the oxidation number is 0. So, for example, if we were talking about the substance of carbon, carbon is just atomic carbon in its elemental form. That has an oxidation number of 0. So do diatomics. So H2, for example, has an oxidation number equal to 0. That's if it's an atom an element in its simplest form, or a diatomic, its oxidation number is 0. The second rule is if you have a monatomic ion, mono meaning one, ion, keyword, the oxidation number is equal to its charge. So if you're dealing with an ionized solution and say it has the sodium +1 ion floating around, its oxidation number is +1. If you're dealing with a situation where you have the chloride ion floating around, then its oxidation number is -1. So if it's an ion, the oxidation number is equal to its ionic charge. Rule 3, nonmetals typically have negative oxidation numbers. However, there's an important exception. So if we think about HCl, for example, hold that thought. Let's do rule 4 first. I went out of order. The fourth rule says that if you have a neutral compound, the sum of the oxidation numbers will be 0. So let's say we have H2O. This is a good example of incorporating a rule from before. So if we think about this one, the very general rule we just learned was that the most electronegative atom in the compound will have its oxidation number equal to its charge. So that would be O in this case, and so O's charge is -2, which means O would have an oxidation number of -2. Now, H2O is neutral, which means that the sum of all of the oxidation numbers have to add to 0. So that means if I have 2 hydrogens, they have to have a charge that add with the -2 to 0. And so that means that in this case, each hydrogen would be a +1, right? Because if you think about it, you have 2 +1s plus a -2, which is going to add to 0. So keeping that in mind, if we go back up to my rule 3, where I went out of order, nonmetals usually have negative oxidation numbers. So if you look at HCl, Cl is your most electronegative. It's going to have an oxidation number equal to its charge, -1. Because we know that this is neutral, the hydrogen has to have a +1 oxidation number because they have to add to 0. Now, if we're using something like NaH, for example, which is actually a thing, this one's a little bit different because in this case I have a group 1, and that was a rule before that says group 1 will have oxidation numbers equal to their ionic charge. So in this case, sodium has a +1 oxidation number, which would make hydrogen have a -1 oxidation number. And what we just saw, is that sometimes an element like hydrogen can have a different oxidation number depending on who it's bonded to. So that's something that we have to keep in mind. Let's do another example under Rule 4 that says the sum has to add to 0 for a neutral compound. Let's say we have SO2, sulfur dioxide. O is your most electronegative atom. That means that O is going to have an oxidation number equal to its charge, and so O's oxidation number is -2. However, there are 2 of them. So that means I have -4, and I have 1 sulfur, which means sulfur has to be a +4 oxidation number in this case. Notice that does not match sulfur's ionic charge, and so it won't always be the case that it does. Kind of stemming off Rule 4, which is that if you have a neutral compound, the sum of the oxidation numbers is 0. If you have a polyatomic ion, the sum of the oxidation numbers will add to its charge. So, for example, the carbonate ion, CO3 - 2. O is your most electronegative atom. Its oxidation number will be equal to its ionic charge, which is -2. But I have 3 of them. So what I really have is a -6, right? 3 -2s are -6. And I know that I'm going to have to add to that some number from the carbon to equal the overall charge of -2. And so if you prefer to call that an X, you very well can call that an X. If you just want to think about it, X minus 6 is equal to -2. What's that? Well, in this case, that would be +4. And so on this example, in the carbonate ion, carbon has an oxidation number of +4. It's not its charge, it's just its oxidation number. Then in a minute, we're going to learn how to use that in classifying oxidation reduction reactions. So that was a lot of rules all at once. And so there's a couple practice that I'll do. So the practice problems say to determine chlorine's oxidation number in these 4 situations. So I'm going to jump out of order a little bit. In Cl2 is a diatomic, which this was the first rule, and so chlorine's oxidation number will be 0. It's probably the easiest one. In Cl2O, O is your most electronegative atom. O is going to have an oxidation number equal to its charge, which is -2. I then know I have 2 chlorines. This is a neutral compound, and so all the oxidation numbers must add to 0, making each chlorine have a +1. And you should say, wow, that's not chlorine's charge. It's not. It's just its oxidation number in this particular compound. If we go back to KClO3, K is a group 1, and so it will have a oxidation number equal to its charge, which is +1. Oxygen's your most electronegative. We know that oxygen will have an oxidation number equal to its charge of -2, but I have 3 of them. So right now I have a -6 from the oxygen, a +1 from the potassium, and a question mark or an X value from chlorine. And I know they have to add to 0. So whether you really call it X or you just think about what X has to be in that case, X in this case has to be +5. And so chlorine in this situation has an oxidation number of +5. What we see so far in these 3 examples is that even though in each one we've been working with chlorine has had a different oxidation number every single time, and that's totally and completely fine. In my last example, I have an ionic compound dealing with a polyatomic, so this one's a little more complicated. I would think about it like this. Calcium is a group 2, has an oxidation number equal to its charge. Oxygen, your most electronegative, also has an oxidation number equal to its charge at -2. But we have more than one of them. We know the sum of all of these are going to add to 0. We have one calcium with a +2. We have 8 oxygens, right? Four groups of 2, 8 oxygens who each have an oxidation number of -2. So that's -16. And then I have 2, be careful that 2 applies to the chlorine. I have 2 chlorines. So if you're going to play this game with the X, which is what I would do, we have to call it 2X. So if we solve this thing for X, we end up with -14 plus 2X is equal to 0. 2X is equal to 14, And in this case, X is equal to positive 7. Chlorine in this example has an oxidation number of positive 7. And again, all 4 of these examples now have chlorine with 4 different oxidation numbers. Another practice, calculating the oxidation number of the bolded element. All these compounds are neutral. Oxidation numbers will all add to 0. In P2O5, O is your most electronegative. O has an oxidation number of -2. That gives me a 5 O's with a -2. That's a -10. And I know it's going to have to add to 0. And I have 2 phosphoruses. So no matter how you think about that, in this case, X is going to be equal to positive 5. P in this case has an oxidation number of positive 5. NaH, we just saw a minute ago. Na is a group 1, has a +1, has to be a neutral compound. In this situation, hydrogen has an oxidation number of -1. In Cr2O7, I missed a charge here, so I lied. This is an ion. It has a -2 charge. I'm looking for chromium's oxidation number. Oxygen will have an oxidation number equal to its charge, -2. But I have 7 of them, so -2 times 7. I know that I'm going to have to add these up to give the charge, which in this case is -2. And I have 2 chromium, so 2x. 2x minus 14 is equal to -2. That makes 2x equal to, what's that, 12? And so x in this case is equal to positive 6. And last but not least, the tin SNBr4, looking for tin's oxidation number. This one's a little easier. Bromine's your most electronegative. Bromine will carry the -1 oxidation number, but I have 4 of them, so I have -4 with 1 tin, so tin will be a +4 because the sum has to be 0. So hopefully that was enough examples for you to have a little bit of an understanding of how to calculate oxidation numbers. The reason for why we use them is to predict who's being oxidized and who's being reduced in a reaction, or if a reaction even is an oxidation reduction reaction. So I'll give you the first example says copper wire reacts with a solution of silver nitrate. So if we write this reaction out, it's a single replacement, so we would get silver by itself. We would get copper. I'm assuming this is copper 2. Should have told you that. My reaction needs to be balanced. And so there's my reaction. So what we do with oxidation numbers is we go ahead and assign them to every atom. And then we see whose oxidation number has changed and therefore who has gone through either oxidation or reduction. So I hope after this example this will make sense. Well, there's a couple easy ones here. Copper by itself is in its atomic form, and so copper's oxidation number is 0, and so is silver's. The other ones we have to figure out. Oxygen, of course, most electronegative, carries a -2. There are 3 of them, so that's -6. Silver is going to carry its same charge as it does as a transition metal, which is +1. And so now we're figuring out what nitrogen is. So I've got a +1. I have a -6, right? 3 groups of -2. And I know that added to some number x has to be 0. So what's that? -5 plus x is 0. And so x is equal to 5. So in this case, nitrogen has a +5 oxidation number. If I do that same trend on the product side, we're going to come to pretty much the same conclusion. Copper is going to be equivalent to its ionic charge +2, oxygen to its -2. I have a +2. I have 6 groups of oxygen with a -2 charge. -2 oxidation number, making it -12. Plus 2 x's add to 0. So -10 plus 2x is 0. 2x is equal to 10, and x is equal to 5. Okay, so I've now assigned oxidation numbers to everything in my reaction. What I'm looking for is whose oxidation number has changed. That's the idea. So we look for the changes in oxidation numbers. If no change has occurred, then it's not an oxidation reduction reaction. if a change in oxidation number has occurred, then it is. And so if we look here, we can pretty easily see that copper went from 0 to +2, and silver went from +1 to 0. Everything else stayed the same. And so that's what we focus on. And so if we think about it, copper somehow went from an oxidation number of 0 to an oxidation number of +2. And the only way that can happen is if neutral copper lost 2 electrons. Right? If copper loses 2 electrons, it would turn into copper +2. And so copper metal is losing the electrons, and the loss of electrons is oxidation. And so this is the oxidation half reaction that's occurring. Knowing that copper was oxidized, we have to know that somebody was reduced, and that's going to be silver. So what happened with silver was it went from a +1 oxidation number to 0. And the only way that can happen is through the gain of electrons. If silver +1 gains a negative electron, it would turn into just silver with no charge. And so in this case, the silver +1 was gaining an electron, and that is the reduction half reaction. So yes, this reaction is oxidation reduction because the oxidation numbers of copper and silver changed. The very last piece to this is that it's often easier to think about this from a net ionic. You don't have to, but it is easier. So the example is a piece of magnesium is dropped into hydrochloric acid and bubbling is observed. And so we have solid magnesium with aqueous hydrochloric acid, of course, still a single replacement forming magnesium chloride, and hydrogen gas. And so this is actually much easier, although this reaction is not that hard. It's way easier if we can think about it from a net ionic, because that's going to very quickly show you the oxidation numbers and thus who was oxidized and who was reduced. So if we think about a net ionic, I have to balance. The HCl would ionize, the MgCl2 would ionize. The 2Cl minus is my spectator. And so this is the net ionic equation that's left. And so this, in this case, is a very simple to see oxidation reduction because the oxidation number of magnesium will be 0. It's in its elemental state, as is H2's. And then because these are ions, the oxidation number is equal to their ionic charge. Hydrogen has a +1 and magnesium has a +2. So talk about simplistic assignment of oxidation numbers in a net ionic. So now we just look at whose oxidation numbers changed. Magnesium went from 0 to +2, and hydrogen went from +1 to 0. Somebody was oxidized and somebody was reduced. Our goal is to figure out who was who. Magnesium somehow went from an oxidation number of 0 to +2, and the only way that can happen is if magnesium lost 2 electrons. This is the oxidation half reaction, which means that the hydrogen must have gained, in this case it's 2 electrons, because if there's 2 H pluses, it would take 2 electrons to turn that thing into a neutral substance with an oxidation number of 0, and so there's your reduction half reaction. So super quick summary: oxidation reduction reactions involve the loss and gaining of electrons. Oxidation is the loss, reduction is the gain. The silly phrase is oil rig. Looking at a regular reaction to decide if it's an oxidation reaction or not, or oxidation reduction, we have to look at oxidation numbers. And so we have a series of rules. If you can assign oxidation numbers, you should then be able to predict if a reaction is or is not redox, and what is the half reaction for oxidation and the half reaction for reduction.